Now it's time to dive back into the meat of the program. And it's my pleasure to introduce Dr. John Jones, an assistant professor of agronomy and soil fertility extension specialist at the University of Illinois. He'll be sharing valuable research findings on the agronomic and economic benefits of improving phosphorus, potassium, and potassium management, as well as their interactions with tillage systems. Please join me in welcoming Dr. John Jones.
All right, perfect. Well, thanks for the invitation today to come and speak to you all. I'm one of the newer faces at the University of Illinois in the Department of Crop Sciences. I'm an extension specialist, soil fertility specialist, and assistant professor of agronomy. I really enjoy the opportunity to get in front of you all and share some of the research that I've done before coming to Illinois, but really how I kind of want to frame the discussion is this is the type of research I'm looking forward to growing in Illinois, and I think can serve our targeted goals of managing nutrients better. So I'll give a personal introduction. If you've seen me talk this winter at all, this slide was probably up. This is just a little bit of where I come from because we're all biased on what our experiences were in science and life and everything like that. I grew up on a small farm in south central Wisconsin. I ended up skipping a few states and going and did my undergraduate at Kansas State University, and then did my graduate work at Iowa State University in soil fertility. I then had a small soil fertility lab at UW-Madison and then hopped back down to Illinois. So I've kind of lived and breathed the central and western Corn Belt most of my life. So I enjoy that work. My lab in general would probably not surprise any of you, focused on optimizing nutrient management. There's a water quality component in wanting to reduce losses, and then there's kind of a precision ag bend on some of the projects that I work on today. When we kind of start into phosphorus and potassium management, again, I want to frame what I'll share today as some kind of a segue through some important points of research that I've led or I've been involved in, and inherently that involves work from around the north central region, primarily Iowa and Wisconsin. But again, I want to frame it as a way of this is what we've actually already started putting together this last fall across the state of Illinois and looking forward to really expanding, and I really welcome your input. I will say, if you have any questions, I'm fine stopping and we can have a little discussion. We can always speed through things at the end of the talk if we need to, so feel free to raise your hand or holler at me if we need to stop. So I'll kind of put this in a framework of where we're at, and I'll show a few kind of general trends, but also a warning with those. The numbers might be a little hard to see in the back, but essentially this is an effort that I led in 2020 and will lead again in 2025, and it's a national soil test summary looking at state-level soil test trends, and we look at potassium and phosphorus, pH, soil organic matter, and things like that. And we aggregate them on the state level, and there's quite a bit of anonymity with how that data is provided. But in general, these are the trends that we saw in the last few soil test summaries in Illinois, a general decreasing trend in soil phosphorus and kind of a number of potassium that bounces around. We see that kind of in the north central region, though, because we do have these west to east and north to south gradients of native K that we find in soils. But just kind of put things in a little bit of a framework when we start talking about P and K. But a note on some of the larger scale trends. So this is just some maps I threw together of soil pH from the soil survey across the state of Illinois. I guarantee you that probably every field you were to throw a dart at on the 0 to 8 map is probably wrong, because it's been influenced by management to a degree that our soil survey maps, generally the trends may make sense, but a given field, it's just incorrect. And so I would take those previous trends into consideration in this context. Now, when we look at things like subsoil properties, this makes a little bit more sense, and I'll tie this into how some of the research that I've been involved in, I think, can be deployed across Illinois as well. One thing, though, as we kind of take a step back, I'm a little bit of a history buff, so I like to collect old, eBay has been a great source for old University of Illinois circulars and things like that, and I've caught some around the department. This is one of the first publications on soil pH testing and lime recommendations that came out from the University of Illinois. But we can improve kind of, again, when we talk about that space-based or place-based management, we can improve what I would term in quotations as precision soil analysis. But we've come a long way from the days where we were mixing trays of soil with solutions out in the field in lab coats. Or I had a friend from Southeast Iowa send me the picture of an infield soil pH probe that you'd stab it in the ground and you'd get a lime recommendation out of it. We've come a little bit ways from that. But some of the concepts are still pretty prevalent. When we look at this relationship between soil test levels and our expected response to fertilization, these are things that probably you picked up in an undergraduate soil fertility class and textbook. These things still hold true, and I'll talk about that a little bit when we think of how the research results can be used in practice as well. So the question then, and I'll hoping I get a few answers here. So we pull into a field entrance and we see this. At this point in the season, what's our game plan? Anyone shout out? What's the first step in this question? Guessing what do we see for a deficiency symptom based off the topic of the talk? Someone yell it out. Brad, potassium deficiency in soybeans, right? So one of the things that I'll kind of split this talk is what are useful diagnostic tools in revisiting what we think of in deficiencies and how we could actually address them. So I think we usually come at, or at least I've noticed in my career, we come at production agriculture probably from two ways, a top-down or bottom-up. I was trained as a soil scientist, and so I come up from the bottom up a lot of times, and I think, well, we need a soil test map that's going to piece apart these different regions. But at this point in time, we're probably going to take maybe a tissue sample or something like that, but we don't really need to differentiate what nutrient is there. We already see the deficiency signal. But one of the questions that comes up, and again, I'll kind of frame the research results here and the questions that I get, are what can plant analysis and what can we learn from what we see from the plant in terms of a deficiency symptom? How do we know what fertilization rate to apply? Do we even need to? And so one of the things, and I'll just show two slides on plant analysis because I think there's a lot of work that can be done, and we're putting together a database around Illinois to have kind of an open access interpretation for soil and plant analysis. These are just an example of potassium concentration in corn with the yellow points and green and for the soybean points. This is a data set that I curated from potassium and phosphorus research that I conducted within Wisconsin. We see relationships with yield certainly when we look at these cases. Now, these were K research studies, so we knew that they were coming, but the interpretation is pretty wide though. Now, I will say in general, you look at these relationships and they may not look too different than the following examples I'll show for a soil test interpretation, but we can start to piece apart a little bit in what we'd expect was sufficiency ranges. Although I think my big summary when I get questions like this around tissue analysis and looking at the plant as a diagnostic tool for phosphorus and potassium specifically. For different nutrients, we may have a different bend on this, but in general, what I've seen in my research experience is they're useful for a site characterization or kind of a post-mortem, what can we find? But in general, they kind of lack the consistency so that we can predict yield response. And so kind of building off of that, we'll get into some of the soil testing and effects that we see in terms of soil test trends over time. One of the things that is certainly true within our cropping systems is we're cycling nutrients faster and at higher velocity than ever before. And it's really yield driven. And that probably takes place is when you're calculating removal rates to maintain a soil test level. Over time, those have probably gone up because our yield levels have gone up. Now, if we look in the next slide, we can see that there's certainly when we kind of throw data together, we do see trends of decreasing grain nutrient concentrations when we get to higher yields. But I think this is probably a function of this data set really, but we see kind of a similar trend in general over time. So we go back to this idea that we're cycling nutrients a lot faster and greater velocity through our agronomic systems. We really need to be able to capture that. And that's where I think this ROI context comes into play, is can we pick up on these annual, biennial, or every 4-year trends to really make a decision that's going to be profitable? So the question that comes up to me again when we think about how do these things all kind of tie in to relate? When we think about removal levels and what we've seen, where we know we're moving nutrients, specifically phosphorus and potassium, through our systems quite a bit faster, do we need to manage corn and soybeans differently in this case? This question comes up a lot. I do a lot of soil test calibration of phosphorus and potassium for interpretations and guidelines. And the question always comes up, how should we manage these two nutrients that are in such a tight rotation within our cropping systems? So one of the quick answers to this question that I'll get, and I'll show some data to back this up a little bit later, is I really haven't seen any evidence to suggest that we need to be differentiating between our soil test interpretations of corn and soybean within our rotations. They really have similar interpretations for what an optimum low and high testing soils are. But one of the things, and this is just an aerial image from this trial that was in Iowa that we did, was that we really need to make sure that we're having corn and soybean prevalent in each year of a study. So I think this is kind of one of the, again, basics of some of the research that I'll share, but also things that I think we really need to build out across the state, because we have really different annual responses of crop level that's going to change how our soil test interpretation is of that data. And so that's kind of one of the fundamental pieces that I think we need to build out across Illinois, and we've got some of those in place already. So now I'll kind of throw out an outline of what I'll work through, and this is really the research efforts that I'll show some examples that are needed to refine and update soil test interpretations. And again, these are kind of textbook basic definitions of the steps needed to do that. They're, slugging through what each of them mean isn't really important. But essentially, we need to go through the process of collection of local data, local responses, so that we can pick apart how soils interact with our crops and our systems around the state of Illinois. This all requires, really the most important bullet point is the one at the bottom. This requires a lot of trials and site years, crops being prevalent and grown in each year of the rotation of the study, and really hundreds of site years to slug through these relationships. And I'll kind of show an example of that as well. This is an example of a data set that I worked with when I had P&K studies that I updated recommendations when we were in Wisconsin. And just shows kind of the trend in relationships between relative yield, or the response to fertilization, and soil test level. What you see on the left is the relationship between relative yield. We increase to a certain plateau and we level off, and then we essentially use some investigation of the probabilities of response to break apart those soil test levels into interpretation classes, low, medium, high, and things like that. But one of the things that's really important, and not a lot of states define this, is we need to really define what's expected of our soils in these given ranges. So let's say we have a low testing soil. What does that mean to you? Should you always get a response to fertilization? Is it 50-50, 75%? Really only two states, Iowa and Wisconsin, actually put numbers to that. And I think that's something that I'm really interested in doing, because then we can say, what do these classes really mean? What do we expect when we say we have a low testing soil and we're expecting a 85-90% chance of response? And so these are kind of the backgrounds and the foundation of what I think will be really useful across the state of Illinois as we build out some of this research. This is just an example from Wisconsin soils. Now, one of the things I talked about and was asked to discuss is ROI and profitability. And I think this is an interesting way of taking this data and kind of inverting it to look at different price scenarios. So when we look at, well, I'll slide back to this slide, we're seeing a yield increase with fertilization as we get to a higher soil test level, or a lower response to fertilization as we move to higher soil tests. What we can do with this data, though, is kind of flip it and look at the net returns, in this case to phosphorus, at different price conditions. Because one of the questions that always comes up is, do we need to be looking at different soil test levels based off of what we're seeing in terms of grain prices and fertilizer prices? Maybe akin to what we do a little bit more with nitrogen when we look at agronomic responses and then adjusting for price scenarios, so that last pound of nitrogen pays for the last bushel produced of corn. Can we do the same thing with phosphorus and potassium? And it's a little bit different animal, so it's really challenging to kind of take that same philosophy and apply it here. But these are kind of some figures that how I like to contextualize it a little bit. What you'll see here is soil test level on the horizontal axis, and you'll see net returns to phosphorus on the y-axis. So this is the yield increase with fertilization, but also taking into consideration the price of the fertilizer. And this was capped at 75 cents per pound of P2O5, bouncing that usually would be about $690 per ton of DAP. And you'll see the corn prices there. I'll show a few of these graphs. As we move from left to right, you'll see a low price scenario of grain prices moving to a high. So $4 bushel corn on the left, and $9 bushel beans as we move to $5.50 and $11, and then $7 and $13. And you can see with the arrows there that we do, essentially what we're looking at in that curve is where we break zero, where we break that zero plane. That would be about the break-even point. And usually that means we're really close, within a few parts per million, of that last pound of P2O5 paying for itself, essentially. Now, what's interesting as you move from left to right is we do see a little bit of change in that break-even point. But if you've looked at soil test data and you've worked with the variability of soil test reporting, these numbers aren't changing a whole lot, at least in the framework of where we might be in a similar interpretation class. But certainly we do see an increase because we have a more favorable pricing scenario. So even though our break-even point is changing from this, what I usually think about it is not necessarily adjusting our target soil test level that we're wanting to maintain, but instead looking at annual rates and how we can adjust those based off of recent prices. And I'll show a few more examples of that. Now this is when we change the fertilizer price. So we keep a consistent grain price, $5.50 for corn and $11 for beans, a little off of what we're at right now. But we'll take two different fertilizer prices and see how that changes as well. And I think this is a worthwhile exercise because we can see how these numbers flex a little bit, and we're not just saying we're maximizing yield, but we're looking at profitability as well. What's really encouraging when we do these exercises, though, is when these numbers or these break-even points match what we see agronomically. I think that's really when we know we're kind of in a sweet spot where the yield response data and interpretation is starting to match what we see in terms of profitability. And this certainly can be done on a farm level, a region level, and things like that. But again, in general, if we go to crop prices and fertilizer prices similar to what we're at right now for DAP, that 24 parts per million or 48 pounds of P would be about the break-even point. So pretty realistic, I think. Now, before we transfer into potassium in this case, I want to kind of talk about the data set that I'm sharing here. So this was data from south central Wisconsin that I'm showing right now. Similar soils, probably as you move about 75 to 100 miles north of here, all the way up through north central Illinois. So kind of take that into context. A lot of Plano, Saybrook, Ringwood soils, Fayette soils as you move west, and similar series to that. But again, I'll show these probabilities of response for the interpretation classes, and I think these are really important because this is what we should expect out in the field. And as you see right here on the phosphorus on the left and potassium on the right, we saw a little bit higher expected or measured responses to potassium, even in high testing soils. Now, one thing that I think we have to take into consideration, again, I think this is a little bit different than what I expect to find in Illinois, is when you move north more towards that glacial retreat, you get higher sand contents and different mineralogy in your even silt loam soils. So I always kind of talk as you move where the glaciers came from, you can hear sand a little bit better in your soil silt loams if you're soil texturing, if you have any ex-soil judgers out there. So take this into consideration. These were very potassium responsive soils that we generally found. This is a description or a general relationship between, again, yield response to potassium and soil test level. Now, one of the things that I think is important to kind of define is that we're talking about yield response to P&K, not absolute yield levels. If we've seen nitrogen data shared, we usually look at nitrogen rate and grain yield. It makes sense, right? We want to increase to a certain point and optimize the rate that we applied. The reason we look at response to fertilization for P&K is we really have three factors that we're looking at. We've got our soil test levels, but we know we need to have a control yield and an unlimited yield in this case. Because we want to know, will these crops in this given soil respond to fertilization? Because it's a long game for phosphorus and potassium. We know we're trying to manage these things over time, and we can bank P&K in most Midwestern North Central soils, unless you're dealing with very specific mineralogy or very low CEC soils. But this was the scenario, and these are the kind of things that I think would be really beneficial to add when we start getting data in and studies out within Illinois so that we can break this apart. Now, this is across many site years of just silt loam and silty clay loam fine textured soils, The idea is, can we bring this apart and make 6, 7 regions of Illinois where we can apply this to? And the question is, will this refinement really change anything, or can we just get to a more granular scale of management? When we look at potassium, again, this is that same type of figure. So we have soil potassium levels, or Mehlich 3 soil test, K on the horizontal axis, and net returns to K. Now you'll see that y-axis is pretty high, so we start to get some really inflated returns to potassium in this case. Those are very, very low testing soils. So when we start to get into soils that are 40, 60 pounds per acre of K. So we kind of take those with a grain of salt when you get to that really high K level. But you can see that in general, we see that same pattern. As crop prices move from less favorable on the left to more favorable on the right, we generally have a little shift in that break-even point. What I think is important when we think about this in terms of how grain markets may fluctuate, how crop prices may fluctuate, is that we really do have some wiggle room to build and draw off that built level if prices are favorable in a given point in the rotation. And so I think this analysis really allows us to go through and say, what are our price conditions at right now? What are we expecting for soil test levels to be at within the rotation, 2 or 4 years, and then kind of build off of from there. But I really think this is useful to start to piece apart. When we go to that same scenario of our fertilizer price changing but our grain staying consistent, we don't see a huge change. And so again, that circle point would be about where we're at for potash in terms of cost per ton. We're actually a little bit lower than that. But again, around that 300 pound of K per acre. Now, I'm not relating this to what handbook numbers are right now in Illinois or what recommendation updates would be in Illinois, but I just want you to kind of conceptualize what I think is some useful data as we start to get projects together across the state. Now, a few questions I always get, and I'll kind of work through a few hot topic questions and emails that I get a little more commonly. We talked about routine soil tests, pretty much Bray phosphorus and Mehlich 3 or ammonium acetate K to this point. But what about some of the alternative tests out there that we have? How do we know that those tests are going to be allowing us to get a value that's meaningful in terms of fertilizer management, P in this case? This is from some work I did in Iowa. You can see corn and soybean response to soil test P, or again, that relative yield. And in general, when we look at these two tests, we have a routine test method, the Bray one on the left, and then an H3A was part of the Haney Soil Health Assessment Tool. This was we did this work when we were getting a lot of questions from NRCS program, or farmers cooperating in NRCS programs, wanting to know what do we do with these numbers because they're not what we were used to when we get a Bray or Mehlich 3 soil test. And in general, if you just look at the amount extracted from some of these tests, we can calibrate them. We can identify interpretations. The organic acids in the H3A extraction have been used in countries like Uruguay since the 70s. So it's not really new chemistry. It's just we need the data for it so we can at least provide some interpretation. Now, the challenge, though, is there's also some other alternative tests and methods that are used in claiming to predict nutrient availability that really muddy the water. So in this case, what happened here, the difference between this slide and this, where actually we have fairly similar patterns between yield response, and we move to the next slide, where there's a phosphorus mineralization technique that was done. This isn't really backed by a lot of soil mechanism for phosphorus mineralization. It's essentially looking at carbon dioxide respiration and assuming if these microbes are active, they must be enacting on phosphorus, organic phosphorus, and making it available. What we see as we move from the left figure to the right figure is we kind of muddy the water. And actually, if you look at the percentages below, we flipped. And now a lot of the soils that are high testing are actually on responsive are on the right in high testing soils. So that's not a very accurate way of assessing response to fertilization. So with these soil health tests, if you're getting them within reports, and if you're wanting to make recommendations off of them, we have to make sure they're independently calibrated. And for this case, we just really couldn't do it. It wasn't a good soil test for predicting phosphorus response. So I get a lot of other questions that relate to how does this work in different tillage systems? So the same process of making a recommendation, wanting to know what's the relationship between soil test level and yield response. How does that work if we're stratifying nutrients, which we know we do in different tillage systems? Oh, for some reason the animation's not working here. Well, I'll summarize what we found here. Essentially, what we found was no real difference in terms of tillage system for a specific soil depth in when we wanted to calibrate that soil test. We really didn't see any difference. The 0 to 6 inch in this case, we would see probably the same with the 0 to 8 inch in Illinois, was consistently the best depth. So one of the things that we often get questions about is if we're stratifying nutrients, do we need to bias our soil tests for where those nutrients are? And the challenge with that is that's not necessarily where our rhizosphere or where our active roots are really powerhousing and taking up a lot of nutrients. That test, that either 6 or 8 inch test really is best performing because it matches where those roots are taking up nutrients. Now there's some discussions about whether we should stratify samples because of previous banding or broadcast applications, and I'll get a little bit into that. But in general, what we saw was not a big difference between no-till or conventional tilled systems. That 0 to 6 or 0 to 8 inch sample would perform the best. However, we did see a little more noise when we brought out into our no-till systems. We saw a little bit less predictability, specifically for corn, when we looked at phosphorus response. And I think that makes sense when we think about how phosphorus cycles in no-till soils. Probably, we didn't really study this specifically, but a little bit of interaction between some mycorrhizal hyphae that we noted within these studies. So we've kind of talked through soil test interpretation, how that relates to yield response. But how will application strategy affect yields, right? We put 4R nutrient stewardship in the title of the talk, so let's compare a little bit in terms of application strategies with different tillage systems as well. Well, let's go back to one of the first R's. The right rate is really relative sometimes to other nutrients. This was a study similar to some of the data that I've shown so far where we looked at phosphorus by potassium interactions within these soils. And essentially the take-home point was that we got to the point where if we were low enough in P or K, we saw a limitation of the response to those other nutrients. So if you look at corn yield on the left, soybean on the right, you see this stair step up when we increase soil test potassium ranges. And the colored bars, or the bars as you move from left to right, from red to gray to blue, are different soil phosphorus ranges. Now with corn, we saw a very nice stair step up where we actually increased yield as we increased soil test K and P levels. But for soybeans, it was a little more muddy. And we see that pretty often when we look at phosphorus response in soybeans. I think because of root architecture and consistency of soil depth and where we're getting those active nutrient applications, we do see a little bit more muddied water when we look at that, but still at a statistical interaction of P and K on both corn and soybean yield in this study. When we think about placement and timing, there's maybe 4 scenarios that we expect. So these are just 4 generalized graphs that what we might expect if we're comparing, let's say, a broadcast and banded application. So on the top left, you see a pretty common result that I've seen in work. We don't see a big difference at all between those 2 applications if we're assessing them based on the amount of nutrients per acre. A little less common, but certainly apparent in some soils and some situations, especially cool springs, where we do see a benefit of banding nutrients at a reduced application rate in an annual basis, not over time necessarily as well. And a little bit less common that we see on the bottom, you may see a reduced yield effect of banded applications versus broadcast, or the opposite where we see an increased yield effect from banded application as well. I'll summarize some long-term research that I worked on when I was at Iowa State with Antonio Mallarino at Iowa State when I was finishing up there. We had some long-term experiments looking at phosphorus and potassium interactions, the placement interactions with tillage. And so these were in 5 research stations across the state of Iowa. We applied different annual and biennial rates of P and K. And so what we really wanted to do was, is there a combination of these interaction of application strategies that leads us to some point where we need to be directing farmers to go? Oh, that's not showing up. So essentially what we found here in this graph is kind of showing up a little bit odd here. We really didn't see any effect of placement or timing on yield response. And essentially what we saw from this was only a rate increase. So for some reason the bars aren't showing up here, but essentially what we ended up seeing was only a phosphorus rate increase. Over many site years, we didn't see a timing and placement change. Now, one of the things, and I'll just move to the next slide, one of the things that we did see, which is really important, is when we were doing a lot of this tillage and placement work, is very few of projects that we've ran into we're actually using a no P applied, but strip till or deep chisel blank. And that's what we ended up seeing in a lot of cases where we'd actually see a benefit to the tillage effect, not the fertilizer placement effect. So something to consider when we're starting to interpret data and I'm starting to put projects together. We always want to keep kind of a tillage blank when we're trying to compare phosphorus or potassium or nutrient placement. These are the soil, essentially the soil tests, the summaries of these kind of 4 management systems over time. And certainly we saw a stratification of the no-till system, and we would kind of expect that, even the chisel plow, when we put broadcast nutrients on. Deep banding did kind of alleviate that stratification a little bit, but when we were no-till deep banding, essentially when we weren't getting soil mixture, we still saw that stratification occur. So, should you adapt a soil sampling strategy based off of your history of nutrient application? This is data from previous work in Illinois by Fabio and Fernandez saying that there may be a need to adjust your soil sampling strategy. Personally, I really haven't seen this being the case though. I think when we start to get to a point where we're, again, fluxing nutrients through our system so intensely, I really haven't seen a consistent nutrient soil test probe in or out of the band relationship or ratio. Now, sometimes we see that ratio present for soil nitrate tests or something a little bit differently. When we were working in Iowa and Wisconsin, we really didn't see a specific ratio of in-band to out-of-band soil sampling. But it's something that is certainly we can take into consideration as we move forward. One of the things that we did also look at was comparing different phosphorus sources. So there's a lot of discussion right now, I would say alternative phosphorus sources, but really they're sources that have kind of been around for a while. So a project that we had and wrapped up was comparing some of the byproduct of a biorefinery that was producing struvite. So essentially a secondary mineral that has ammonium, it has nitrogen, phosphorus, and then also some magnesium as well. When we compared these, we really didn't see any difference in phosphorus sources. It was all of a rate effect. So in terms of solubility of triple superphosphate in this case compared to struvite, they were very similar in terms of when we did the nutrient analysis, and we saw an increase in soil test levels that was the same for both nutrients. We were able to say that, yeah, you can go and use struvite as a P source, but if you're hunting for it, it can be kind of expensive. And now I know there are plants that are making struvite out of MAP that's being brought into the U.S. One of the other questions that we get, again, kind of back to this in-season management and where we see deficiency symptoms, is there a benefit to in-season potassium applications? This was an example, that same picture I showed. This is a poorly drained joy silty clay loam soil, and that would be kind of prevalent in northern Illinois and southern Wisconsin. And as I was driving home one day, I kept seeing these potassium deficiencies. Oh, I guess we're not showing up here how we're supposed to. So the in-season K, essentially what this was a study to look at we'll just move over here, a study to look at the effect of side dressing potassium on corn and soybeans as well. We side dressed with potassium acetate at growth stage V6 for corn and R1 for soybean. What we saw, we really wasn't a huge revelation by any means. We saw a response to side dressing potassium in soybeans only when we were at a low enough testing scenario. Now this project came about in 2023 when we were facing fairly dry conditions in the southern part of Wisconsin. And we really wanted to say, can we alleviate or recover any yield loss from potassium deficiency? And I would say the answer easily is no, you really can't fix a potassium deficiency that you've already seen. Usually we already have organic acids that are building in that plant, they're burning tissue, because that's what K does. It balances the charge of some of those organic acids, and they burn that plant. But we did end up seeing that in low testing soils, or if you were in a situation where kind of an unstable land tenure was present, we did see a response to only about 55 pounds of K2O in low testing soils that did lead to a yield response. So that kind of led to the question of, was it worth it to try to look at in-season K? There's another project that's going to be coming out of this. What I would say is it probably usually doesn't make a lot of sense because of the logistics of wanting to get any fertilizer on. And if you're applying a liquid, it does require a fairly high carrying load in some cases if you want to get a lot of potassium out. So there's a lot of challenges with this. When the soil is tested, to make this interpretation or recommendation is also a challenge. Again, this was the season and the growing season in 2023 when we did this work. A smoky day from the Canadian wildfires, and we did see some potassium deficiencies that easily popped up in our low testing soils. Now, when we think more about soil test levels, but then also yield responses at different application strategies, one of the studies that Dr. Grade Steckel started at the Monmouth Research Center that we're working on now was a comparison of different application strategies for P and K. So in this case, essentially we had a control where no P and K were applied, and annual P and K rates. This is all based off of removal data. Biennial, so every 2-year rate of dry fertilizer applied, and then some combinations of either the P or K was applied to the corn or soybean individually. And in general, we saw these systems can flex. They really can, and this really kind of matches what I think you're seeing hopefully in the talk so far, is that our corn and soybean systems really can adapt to when and where we're putting those nutrients on. We really don't see this tight window that we need to get nutrients on within a case where we're limiting. Usually, if we're low enough in soil test levels anyway, we're limiting yield by a different mechanism than a lack of fertilizer. And so when we look at the data just from the last 3 years that we've worked with Greg, and we're working through it back all the way to 2017, we saw that we really didn't see a change in when we were getting that P or K out for corn or soybean yields. And these results held true back through the rest of the study. The only thing we're seeing is a response to fertilizer at some point within the rotation. So the final point or kind of the final theme of the talk is how we relate some of these yield responses or profitability responses to soil test P or K management. We'll talk about P specifically, how that relates to nutrient stewardship practices. Are there abilities to kind of hone in on specific P management strategies that lead to a higher ROI, but also a reduction in phosphorus losses? So we did a lot of P loss work in Iowa, a lot of rain simulations, natural runoff collections, and I'll show a little bit of that data as well. So this is an example of integrating agronomic and water quality assessments. This is a continuous runoff study that was in the northwestern part of Iowa. The study went for 6 years, and it was a corn-soybean rotation. Again, corn and soybean present every year. Comparison of tillage and then P management strategies. So fall broadcast versus spring banded applications at multiple rates. And you can see the studies here as we look at them. We had control plots where we were collecting runoff continuously from the entire 8 rows of the corn or soybean plot. And I apologize again for these graphs kind of coming up weird here. But you can see the numbers and the statistical difference on some of them. So in general, when we average across these in terms of yield response, we didn't see any change for how our soybean yield responded to these management. Again, no matter when we put the P on, no matter what tillage system, the soybean was pretty flexible enough. Now you kind of see a gradient as you move towards the no-till system. So again, we had conventional tilled systems, no-till, and then we did have a no-till and cover crop treatment that was high testing P soil. And so even in that high testing P soil for the no-till cover crop, we did see a little bit of a yield reduction, but it wasn't statistically different. When we go over to corn, we really just saw a benefit of the tillage systems here. Again, this is in northwest Iowa, where essentially we were getting to a point where getting dry and warmer soils was paying off most of the time. And again, sorry this isn't showing up here, but you can, I guess, see the letters. One of the things that we did see very clearly was an effect on phosphorus losses. So we saw a benefit of putting that P below the soil surface or incorporating the P if it was broadcast. Really, the biggest takeaway was, and actually the best performing system, was a banded P application in the conventional tilled system. That's when we reduced the most amount of total P loss. Now, if you look at the total P category up in the upper right, you see the little number C. That was actually for the no-till cover crop system. Even in a high testing soil, we actually did get the lowest total phosphorus loss when we had a cover crop but no P applied. So probably when we think about the best tool to reduce P losses in the framework of fertilizer management is to just avoid these high testing soils and getting them to draw down back into our maintenance or optimum ranges. That really was the case. And in general, now within these loads of losses, we're only losing about 1.5 to 3.5 pounds of P2O5 per acre. So not an exorbitant amount of P is lost, but over time, especially if that's in a soluble form, it can lead to some water quality issues. One of the things that, again, we'll kind of harken back to the soil test management concept is that this is the relationship over many studies within the state of Iowa. We looked at the relationship between soil test level and nutrient concentration and runoff. Now, we see a clear linear relationship, and this really does drive quite a bit of policy decisions around soil test phosphorus management, P management, and water quality. But one thing that's really important is when you are between kind of that agronomic optimum range, essentially between about 0 and 30 ppm, it's really a shotgun spread of data. It's kind of hard to see here, and this is in the 2-inch sample depth, so it's a little bit different than we'd interpret for an agronomic sample depth. But this is really important that when we're shifting, let's say, agronomic targets for soil test levels, and we're still below 75 parts per million of phosphorus, we're really not influencing that massive P loss. And so when we think about kind of having some confidence in adjusting phosphorus soil test interpretations, I know I just worked on the Wisconsin's data set and we increased them. We weren't increasing them to enough where we were losing more P, essentially. And this connection is I think, really important to keep between an optimum range for agronomics, but then also water quality as well. This is a summary of hundreds of rainfall simulations and dozens of trials around the state. And as we apply more P, we lose more P, right? Not really a big surprise. But in general, that 50-pound rate is about what our removal rates were in most of these systems. We don't see a big difference between not applying P at all and applying right at that removal rate, where we're kind of in that sweet spot for agronomic optimum management. So we know we have a higher ROI there from those relationships of break even, but we also have an environmental benefit that's real and tangible. And when we look at this in terms of tile drainage P loss, this is from a study in northeastern Iowa. We look at that same relationship between soil test level and the P loss and tile drainage. We see that when we're about at that agronomic optimum, we're not really having a big shift in the amount of P that's lost with drainage. It's only when we start to get into those very high testing soils. One of the things that I think is really important, and we're kind of wrapping up here with a few slides, is that long-term trends are really required for a lot of this data to get put to work. Going in and taking, as you can see, the infrastructure to do a lot of this work is multi-year and takes a lot of effort to establish and get going. And long-term trends are really how we start to piece apart whether effective management is taking place. This is an example of a relationship between soil test levels changing over time and the amount of removal. And as expected, you can see decreasing soil test K on the left vertical axis and the cumulative crop removal on the right. As we would expect, we're reducing soil test K levels with consecutive removal of grain in a corn soybean rotation. And one of the things that's really important is that little 10 pound of K removed per part per million, or 5 pound per pound of soil test K, and then we had 5 pounds of removal per soil test K there. One of the important things about this is that those numbers are in the background to any build calculation or assumption or drawdown. And we don't have time to go through it today, but that's really something that I think it's important to look at, because some of my work is showing that the rate that we can move soil tests up is not equivalent to the rate we can move them down. And that's kind of baked into almost every fertilizer recommendation in the north central region, is that we assume it takes the same amount of fertilizer to increase soil tests as it does the same amount of nutrient removal to reduce them. And those kinetics are just very different. Where we're putting fertilizer, phosphorus, for example, into soil on the physical components of soil is very different than where we're extracting it as a crop root. Potassium, I would say, is even more divergent. It's even more of a case where there's separate mechanisms that are happening there. So in summary, I think regardless of price conditions, functional agronomy is really the key. Probably not, this isn't the most sexiest talk saying soil test P and K management is exciting, but we need this fundamental data to kind of work through this and have a good system that we can have a lot of faith and trust in within the science that's providing interpretations. And especially for phosphorus, we need to have these relationships and these long-term efforts to have confidence that our agronomic recommendations are going to give us the environmental outcomes that many people outside of this room and outside of ag really want from our phosphorus management, for example. So in terms of, I really think the last bullet point is probably the strongest here. Long-term agronomic ROI really has a strong relationship with positive environmental outcomes, but we need more data to show that within Illinois. Within that, I thank you for your attention. What I wanted to show a few times a few points up here were some ongoing research trials that we've got going this fall as well, but are going into 2020, this past fall, but are going into 2025. If you're interested in collaborating or just telling me things that you really think should be worked on in your neck of the woods, I'd love to have a discussion. One of the things that I'm really passionate about is getting our group around the state and we're willing to travel all corners of the state and do work. Where's Blake's in the back corner there? He's soil sampled with me a few times already in the fall. We're definitely wanting to make sure that we do soil fertility research that gets down to a granular level for interpretation around Illinois. So again, thanks for your time. There's my contact info. I can take some questions now, but if not, I'll be around the rest of the day as well. Appreciate it.